All right, folks, good morning. So on Friday, we started discussing domain and range, and where we left off in our conversation is that a solution to a function are ordered pairs. And we had a picture over here of just any generic line and talked about how literally any ordered pair on this line counts as a solution to a given equation. We discussed how there are an infinite number of points on that line, and also reminded ourselves that solutions can be found by making an input-output table, XY charts. And lastly, we discussed that domain is my set of all possible x values, and range is my set of all possible y values. So to start off our notes for today, we're going to discuss different ways of writing domain and range. We have three specific ways. We can use words, such as x is all values greater than 2. And then we have these two options, interval and set notation. Who has a vague memory of interval and set? Interval is a combination of brackets and parentheses, and then set, we have some curly Q brackets with some inequalities going on. I see some shaking heads of yes, that's great. So for right now, let's just get these three titles, and then we're about to look at some examples. Good? Go ahead and get those three from her. Okay, so we need to keep in mind the following, and I'll give you a moment. Okay, so interval notation, as we discussed, is going to be a combination of brackets and or parentheses. So for my domain, I'm going to find the most left value and come in from the left and then come in from the right. For my range, which is all about my y values, bottom and top. So right now we're laying the groundwork for all of the tools that we need to write our domain and range, and then we're going to practice. And by means of practice, we'll see it. Remember that I did pass out a handout of certain slides that are printed, so that when the graphs come up here, you don't need to copy the graphs. So when you have a moment, find that slide from that handout from Friday. So by closed circle, we literally mean a closed circle. Closed circles are associated with, what is this sign? How do I read this? This one? There you go. Less than or equal to. That line underneath represents the or equal to part. So this is less than or equal to, making this one greater than or equal to. And what's the name for this? What is this called? Brackets. So that's the term we'll use for those. Open circle literally means open circle. Open circles are associated with strictly less than. Notice we do not have a bar underneath. So open circles are connected to strictly less than, strictly greater than, and what are these? Parentheses. Now, the key difference is right here. If I use a closed circle, a bracket, or less than or equal to, greater than or equal to, we're saying that that value is included. If I use an open circle, it means that that number is not included. So to give you an example, if I wrote x is greater than or equal to 5, can x be equal to 5? Yes, x can be equal to 5. It's included. If I say x is greater than 5, can x be 5? No. So x can't equal 5, but could be 5.0001. So literally the next possible decimal right after 5. It can't be 5, but it could be 5.000001. See the difference? Here x can be that value, here it cannot. Just infinitely close, just not equal to. This will be a key note whenever we see arrows. Parentheses are also used when the graph approaches infinity, meaning the graph keeps going on forever and ever. Anybody remember how to draw the infinity symbol? Ooh. It's like a sideways 8. Another fast way to draw it that comes out neat is to literally just draw two O's side by side. Comes out nice every time. So this will apply to whenever we see arrows. Because arrows imply that the graph keeps going forever and ever and ever. Yes, Winta? Mm-hmm. Sorry, I ran out of space. But x could be 5.000001. So it can't be 5, but it could literally be the next possible decimal right after 5. Ready to practice? Okay. So, let me know when you're ready. The next example will be an ordered pairs example, as you just saw. So go ahead and look at the table, which was the second question on the homework, because tables and ordered pairs and maps are all approached the same way. So go to the first page of your homework from Friday on the very front. Number 1 is a set of ordered pairs, yes? So how we approach the ordered pairs is how we're going to approach all 3. And I see many of us do remember how to list domain and range for those, so that's very nice to see. Are we all set? Okay. Michelle, help her out with the rest of the notes if she needs it. Okay, so decide if the relation is a function, and then determine the domain and range. What does relation mean? What's a relationship in the real world? Two things? What about two things? Are together, they have a connection, right? So everything is a relation. Not everything is a function. Remember that. Everything is a relation because these points are connected. It doesn't mean they're a function, and we're going to see what the difference is. But first, let's see what's domain and range. Thoughts on how I'm going to write domain for this? Sure. Very good. So what would that be? What would that look like? Is -7 an x value? Careful. I agree with you, you're right. But I think -7 is sitting in the y spot. Okay, so not from your homework. Use what you did. So the approach in your homework, apply to this. So what would my list of x values be here? -2. And as you go, you can just lightly cross it out. Don't scribble it out because you want to be able to see it. But lightly cross it out. Okay? Great. Who wants to take on the range? Cassidy? and we're done. So I'll give people a moment to write. When you finish, take a look at how you approached the ordered pair question on the homework. We have lists. That's good. It's exactly what it should be. Have we finished answering this question? Yes, Cassidy. Yes, so curly brackets indicate a set of values. So in any textbook, you would see those curly brackets used. Great question. Have we finished answering this question? What part have we not addressed yet? Is it a function? Any ideas on this? Yes. Is it? How do you know? Very good. So a quick check. Do you see any repeating x values here? No. So automatically, yes, this is a function. You could either tell me because no x values repeat. I would accept that because it's not technically wrong. But the more specific answer is that because each input inputs refer to x or y's. X's. Because each input is sent to exactly one output. So this one is not technically wrong, and it is the reasoning behind why we can write this. Yes? Tell me exactly what you wrote. It has only 1 point on the line. Are we thinking vertical line test for that one? So keep that in mind for continuous functions. That definitely works. But when we have a discrete or countable set of inputs, we physically have to check where each one is going. Now, one thing I would like to caution you about, and this came up when we did this with some of the level 2 classes, if they saw this, let's say this was the point here, is this a, pretend I didn't have this one. If this was my set of ordered pairs, is this a function? Ooh. Where's 5 being sent? Where's 5 being sent? So in both cases, is 5 being sent to the same place? So if you were to think about what would happen if you were to graph this, right? You would graph 5, negative 4, and then you would just graph 5, negative 4 again right on the same point, yes? So if you see x repeating, that's a red flag. It's not an automatic, not a function. You really would need to check. If we had this, is that a function? No, because you would graph 5, negative 4, and then 5, 0 would be right here, and what test would that fail? Right. It would fail that test. So if x repeats, it's a red flag. It is not an automatic, not a function. Okay, very good. Let's move on to our next example. Mappings. So this is a good example of where I do not necessarily expect you to write word for word, summarize, okay? So when we have ordered pairs, a table, or a mapping, you will always use set notation. And by set, we mean the curly brackets with the list. And now we have our next example. Can someone take out that handout from Friday just so I can make sure of which ones are on the photocopy and which ones are not? I just want to make sure I give you enough time. Okay. So this one is on your photocopy, right? Look on the back. Voila. So take out the handout from Friday. You don't need to write it down. It's fine if you have. I would make a note, see handout, and put it in a little box. So in your notes right now, see handout. So we do not need to copy this map because this you do have. So this is not all one example, okay? These are two separate examples. So let's call this one number 1, and this is number 2. So let's decide, is number 1 a function? Yes or no, and why? I hear a vote for yes. What do you think, Jasmine? What's causing you to pause on it? Yeah, the fact that -1 and 0 are going to 2? Very good. So this is okay. Imagine that these points represent you guys. Can 2 of you have the same A period class? Yes, that's fine. In fact, all 1, 2, 3, 4, all 5 of these points could be sent to 2, and that is okay. The definition of a function is that each input is sent to exactly how many places? 1. So how many places is -1 being sent? Just 1. How many places is 0 being sent? Just 1. If it happens to be the same point, that's fine. Yes, this is a function. Each input exactly 1 point, 1 and only 1, however you choose to say it. When you're ready, decide about number 2. What are our thoughts on number 2? Who have I not heard? Olivia? Why is it not a function? Very good. So if you have a highlighter, I would highlight this. Make this stand out in your notes. This is where it fails, 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 fails. No bueno. No. Because as Olivia just said, no. Because 4 is being sent to how many different outputs? 3 of them. 3 different outputs. And if you wanted to be specific, we can list them in parentheses. What are the 3 outputs it's being sent to? Definitely not okay. If you don't have your highlighters yet, borrow one from somebody around you, okay? Can you lend him one of your highlighters? You have one? Oh. Highlight, highlight. The more interactive your notes are, the more likely you are, 1, to learn from them, and 2, to actually use them. A month from now, if you don't highlight this, it's not going to stand out to you. Okay? All right. This one is also in your handout, so make a note if you want to see handout, but we're going to focus here. Okay. So, for domain, think smallest to largest from left to right, and for range, think smallest from bottom to top. Now that we're starting this conversation, is that sounding more familiar to some of us who didn't remember it from the beginning of class? Thumbs up, middle, or absolutely not? Give me a vote. Thumbs up. So would be halfway, and then down like absolutely not. All right, so I don't see that many thumbs down. Okay, good. So this is strictly for note purposes, okay? So is this a discrete or a continuous function? I heard half and half. So discrete is countable. Discrete would be ordered pairs, maps, and tables, which means that this is, what's the word? Continuous. So when you hear me talk about continuous functions, this is what we're discussing. Lines. Discrete is countable, it's fixed, it's a set number of values. Continuous, a whole nother world. But we learn by practicing, so let's practice. Let's first talk about domain and range of linear functions. Can I see the other side of that? Okay, so this goes in your notes. Notes. You can draw any line you want. It does not have to match my graph. Your line could look like this. I don't care. Just draw a linear function in your notes. You don't need you don't need to count 1, 2, 3. Just get me a straight line, please, with arrows on both ends. What's the formula for a linear function? Who remembers from last week? Good. So we're talking all things linear, all things y equals mx plus b. Let's talk domain. When I come in from the left, I stop right here. This looks like negative 12, but is it? No, why not? Keeps going forever and ever and ever. Forever and ever and ever in that direction is what? Which kind? Negative. Why did I put a parenthesis right here? Can you equal infinity and negative infinity? No, literally goes on forever. Now, I just came in from the left. So if you want to, you can put a little L. That's from my left. Now I'm going to come in from the right, and I'm going to stop right about here. Is that 10? No, what is it? Good. And I put a parenthesis again for the same reason. We cannot equal it. Is this interval or set notation? Good. This is interval. Set notation. And again, if you have highlighters, what I do in red, I would highlight. Set notation has a very methodical approach to it. This middle piece will never change. Because if we read from the middle, we're seeing x is greater than something and x is less than something. Our job is just to plug in what those two things are. But this setup never changes, ever, ever, ever. What am I going to put in this left spot? Good? What do I put in this spot? Infinity. Done. That's it. Do I need any lines underneath these inequality symbols? No, because we are not equaling infinity on either end. So for domain, I came in from the left and right. For range, what am I going to do? Good. Come in from the bottom, what do you hit? Come in from the top. So she got negative infinity because I come in from the bottom. Da 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 da. Looks like it would be maybe be like a negative 7, but what does she see right there? An arrow, and an arrow going down forever and ever. Negative infinity. Now when I come in from the top, ooh, 14. Am I right? No. Why? Another arrow. So what's that going to be? Infinity. Oops. Okay, so let's get set. Same thing, except just change out the x's for the y's. And again, this middle piece will never change, ever, ever. We're saying y is greater than a value and less than a value. Can someone tell me what I should put on the left side? Good. Negative infinity, positive infinity. This is true for all linear functions always. The domain and range for all linear functions will always be this. Another way of representing this is all real numbers, which is a really funky R. Draw two vertical lines side by side and then make it an R. That means all real numbers. Yes, but wasn't it? So her question was, can we just write this every time? The answer is yes, but how much fun was it to go through set and interval notation first? I know, right? So yes, you could represent this as all real numbers, and this is also all real numbers. And again, this is always true for linear functions. Okay? Very good. Move on to our next example. This should be in your handout, yes? Fantastic. I challenge you to do this one on your own. Come in from the left, come in from the right. Come in from the bottom, come in from the top. Looking for set and interval notation, please. Yes. Correct. This is a solid dot, and this is a solid dot. So is infinity going to be any part of this graph? No. We are looking for set points, and you then also need to make the decision bracket versus parenthesis. One tool that can help, if you take your pencil, this red line is going to represent my pencil. You can physically take your pencil and come in from the left side. Tell me when to stop. Where are you on the x-axis? -6. So if you find yourself struggling to see where that point is, you can take your pencil and do that. Is that going to get a bracket or a parenthesis? Good. And just to finish illustrating how to use your pencil, you just came in from the left side. Now where are you going to come in from? Right side. Tell me when to stop. Okay? What's the question I'm going to ask? Where are you on the x-axis? Because sometimes what happens is people will say, ooh, 3. But what is 3? What kind of value is that? Right. Domain is all about x. So we don't care about 3 right now. That's where that question, where are you on the x-axis, is so important. And what was the answer for that again? 8. Good. Bracket or parenthesis? Good. I'm going to rearrange my pencil to come in from the bottom. Please work on the set notation piece while I do that. And then we can compare. When you're ready, check your set notation against my set notation for domain. Do we match? Notice, what did I draw underneath my inequalities? Why did I have to put these little lines? Very good. It can equal 6. I have a closed dot, which means this ordered pair does exist on my graph. 8 is a possible x value. If this was an open circle, it means that my largest x value would be like 7.99999999999. But can it be 8? No. Good. And here I have moved around my pencil. So we came in from left and right. Now how am I going to come in? Bottom. Bottom and then the top. So you can again physically take your pencil, put it like this, like just like my red line is. Come in from the bottom. Tell me when to stop. Good. Where are you on the y-axis? Very good. And then I come in from the top. Tell me when to stop. Good. So let me record that -7 before we talk about the... Does this get a bracket or parenthesis, by the way? Bracket. Even though I don't see a solid dot, remember that a continuous line is made up of points graphed so close together, you can't see the space in between. So technically, I have a point right here, and I have a point right here, and I have a point right here, so close together. So that's solid. Okay? Okay, let's go back to talking about this top value. Guess what value people tell me all the time by accident? 3, because they see this point right here. But my graph goes higher than that, which means there is a higher y value. Hence the importance of, if it helps you to visualize,